Yeah, thank you so much for coming. It's good to see you here at this session that is an applied session, mostly from industry, but not only. In fact, Dragos and I, that we organized this, I'm Alberto Speranzan, we not only wanted to have industry, but also some representatives from the government, and we're happy to have someone from DARPA actually presenting some of the work that they are leading on in Neural-Symbolic. And the idea here is to understand what industry is doing, what kind of challenges we are facing. So we hope that is an interactive session. I don't know if you want to say something more.
Sure. So I've been part of this community, invited by Arthur since about 2008 or so. And one thing that I wanted to commit is I'm working hard with my company to make available not only data sets, but loss functions and simulations, especially for NeSy. It's a community that I value a lot. In fact, I think pretty much all practical systems where you have deployed learned models and so on are right now Neural-Symbolic, or they have some Neural-Symbolic components. So welcome here, and I hope that this will continue with in the next years. So, okay.
All right, so we can get started. So the first talk will be actually from Dragos and Dennis about decision making for air traffic deconfliction. So, yep.
So that one is for questions. Okay. So Dennis has done virtually all the work in reinforcement learning. I'll give an overview about building on what Jan started on the first day. So that's the long-term vision. We want to have these real-world systems that make decisions, planning, dialogue, and so on. I work on an autonomous airplane. And finally, we can talk about it. You'll see also a video. And you'll see a small function described by a Neural-Symbolic function developed by us. Probably all of you, especially grad students, think that this is how it works. There's some perception, planning, and so on. They're thrown out. Jan has presented you that beautiful slide with a vision on a full agent. I'd like to tell you how things work today, and this is how things work on cars, on airplanes, on iRobots, and so on. And I'd like you to think about this when you think about your learning problem. Basically, it's very simple. At the middle, you have a decision stack, your planner, and what's important is the low level, this is the control, and so on. High level in the planning is, the high-level decisions. The huge difference is this. At low level, low dimensionality, high frequency. So decisions have to be made fast, 10 hertz, 30 hertz, 60 hertz, whatever. At high level, high dimensionality, low frequency. So think about what you want to do tonight. This is what we have to balance. Typically in this stack, you have the hierarchy of planners that Jan has shown us. So here they are. And here is what we have knowledge. Think of maps, domain knowledge, and so on. Perception, dialogue, and so on is here. And here is your actuation, your interface with the system that you're building. As simple as that. What you'll see today is actually, so machine learning sits everywhere. You saw Jan, and you saw also Leslie's talk, right? What you'll see today is a machine learning system that sits somewhere there above the low-level control for an important problem in aviation, actually. In aviation, detect and avoid, or sense and avoid, avoiding an intruder or multiple intruders that are not aware of you. So they're not adversarial is a big problem, and having guarantees on it is actually a big problem. We took on it, and we deployed it on an actual airplane, and Dennis will talk about that.
Hello, everyone. I hope that you can hear me fine. So yes, so I'm Denis Osipchev. I'm with Boeing, and I was working on this RL-CAS system for several years. So this system is the purpose of the system was to avoid collision avoidance, to avoid collisions, potential collisions in the air. And it was all machine learning based. It was using reinforcement learning agent. So you can see on the picture here that so the original plan was to use just single obstacle, but at the later stage, let me use another one. Yes, at the later stage we used actually 2 obstacles and problem become much more interesting. So on the picture on the right you can see 2 airplanes. So like when we started this effort we already had in mind that we would go through the demonstration. So we planned to demonstrate it on the real airplanes, flying them. On this picture you can see 2 airplanes. One is on the left is a diamond which served as a intruder, which was basically causing posing collision risk, and on the right side it is our autonomous demonstrator, so Cessna Caravan, which is not fully autonomous, but we use it a lot as a demonstration platform. Yes, so so the RL agent that we used was pretty straightforward. So it was a fully connected MLP agent, which we trained as soft-target critic, and it was using continuous inputs for the system. Basically, it was a dynamic state of 2 aircrafts or of 3 aircrafts when we done 3 aircrafts. So the dynamical state was like simple, like distances, speeds, accelerations. But like you have to understand that it was not fully observable system, right? So like there are still some parameters missing in this, so which need to be guessed and generalized across different states. So so here's the main diagram of the Neural-Symbolic kind of solution, and I talk about like why we treat it as Neural-Symbolic later, but now. So the RL agent sits in between, so it is like trajectory prediction and surrogate policy model. So the RL agent was trained beforehand, so we trained in simulation, and we deployed with using ROS interfaces to the real airplane. So the real airplane was getting data from ADSB, and the data was converted into the right format for the RL policy. Then the policy was rolled out with a prediction, and the airplane would receive back the full trajectory, right? So, which is easily accepted by the autopilot, and like this actually handles most of the issues with mismatch in dynamics. Like since we trained on a surrogate, right? So there is obviously some difference in the dynamics, which was handled by the controls mostly, right? And since we had some. Again, like some demonstrators in mind, so we basically come up with a set of rules and set of parameters for the training. So those parameters were slightly more relaxed than the actual dynamics of the plane, so we can guarantee that the airplane would be able to follow it. On the right side, you can see that there was like step responses from the actual airplane. Responses to the step inputs, step commands, right? Which we did on the test. So as I said, that controller was handling most of the issues, especially like with turning rates and like airspeed. But like even then, we still had some issues with like latency of the controller, and we had some accumulated error as a result. So this was basically one of the reasons for the system, potential reasons for the system to fail, right? So another reason to fail was the RL policy itself, right? So we all know that like RL policy, most of the time it does not converge to 100% performance, right? So there's always like 99% of the cases where it can perform reasonably well. And often we don't really know how to explain those stuff. On the right one, you can see that it is basically statistics for failure cases, even in surrogates, right? There is like, even if the dynamics is perfectly matching, there are still some conditions, like 1% of the time in some certain scenarios when we cannot really explain why the system fails. So, and the reason, or like the way to to avoid it was actually introducing top layer logic, right? Basically making the system Neural-Symbolic. Right? So we have a set of rules which are constantly changing the solution provided by the RL agent. And if those rules are violated, it would either call for another request another solution, or it would switch to alternative solver. Right? So this worked really well, but we demonstrated on one collision or one intruder and then on two intruders, but we know that like potentially we may have like infinite number of intruders, and since RL agent cannot really handle it and cannot scale up well, so we need to find another solution to deal with scalability. Right? So this is where the system become hierarchical. So we have a higher level planner now, which can switch between different intruders and prioritize different intruders when it is trying to avoid the collision. Or so that's one scenario, right? So when we have basically multiple objectives, so multiple intruders we want to avoid, but we have a single policy and we just switch in the inputs. So there is another side of this aspect is like when we have multiple policies but single objective, right? So in this case, we may switch the policies to find the most optimal one. So this one we would use in the case, for example, like if there is a like dynamics is changing on the plane, right? So we know like dynamics of the airplane is changing with respect to like the altitude, on like with respect to the temperature, different flight envelopes. So it is not a constant thing, right? So we may want to switch between different solutions corresponding to those parameters as well. So here's an example which we are currently working on the multi-agent specifically, right? So how we handle multiple objectives. So in the plan is, again, like we still use the low-level RL policy to avoid one or two collisions, but we can now scale to infinitely many objectives by just switching, basically like rewiring the inputs. So, and here you can see the prototype, which we done with another Boeing colleague of mine, where we try to optimize assignment in this case, right? So we know that like we have a policy for the what we call like 1v1 or 1v2, right? Collisions, and now we're trying to optimize the policy with respect to 1vn, right? So if you have, potentially in some cases, we may have multiple agents trying to avoid multiple collisions. So in this case, it would be like MVN scenarios. And to do this, we can, what we proposed was we first group the agents into certain groups and then group the tasks and then do the optimal assignment using Hungarian optimization. So the cool feature about this is that we done Hungarian optimization based not on the simulated results, but actually based on the value estimation which comes from the reinforcement learning actor-critic architecture, right? So, and the value estimation is basically showing us like with which success probability we can complete certain task. So in this case, in the optimal assignment part, we optimize the global assignment where the multiple agents try to accomplish their multiple like set of tasks, right? So, and on this slide you can see actually the final simulated trajectories where we had 10 agents trying to solve 10 different tasks. So we done the assignment and they independently basically perform the tasks. So and next I have a nice cool video of real flights that we've done on the caravan, on the autonomous caravan. Wait a second.
We're here at Grand County International Airport.
We're here to do flight testing of some really, really innovative flight software functions using neural nets to generate avoidance maneuvers in collision avoidance scenarios.
machine learning algorithms, AI in general, require assurance. We want to know that the algorithms stay safe, basically, in the decisions.
Building trust that the general public actually has in pilots and shifting that trust to automated trust. How do we do that?
That's straightforward right now. In our flight test, we're going to have a neural net try to reroute our Caravan autonomy demonstrator around a second airplane that's headed right for us.
I got a visual. This isn't something we're doing back end on the ground. We're doing this in real time on the plane. Hey, there's an intruder that's this many nautical miles away on this heading, and the AI will spit out, this is how you avoid it.
The system gives us a course to fly around the intruder and the weather.
We have a learn procedure which is optimal that avoids this airplane. Now we want to know that it stays safe in different conditions that cannot be anticipated.
The reinforcement learning itself is optimization. And from optimization perspective, it is a very complex task when you need to come up with a trajectory which would avoid multiple intruders.
It makes really intelligent decisions that pilots would make, and it's surprised us a few times with how it's decided.
Looking at
Can you still hear me? Yeah, I think the main purpose of the video why we showed it was you can see that how many actually people involved in making all of those systems apply to the real life tasks, right? And this is something what we want to encourage you all here to basically collaborate with us, collaborate with experts maybe in other domains, right, to apply the systems that you're making to the real life applications.
And yes, we're hiring both in Europe and the US. Talk to me. To thank our team, Boeing team, ARPA Achieved Autonomy, then Alessio Lomuscio, who's here, Darren Kofer, Claire Tomlin, Forrest Lane, and Tom Dietrich. All of them contributed with diverse ideas towards this. As you see, we test in the snow, we test in different kinds of weather. Always when we test, we need people and so on, so it's high-risk testing, which requires a lot of infrastructure. So if you want to work on something cool like this, talk to me or to Dennis. Thank you.
I don't know if there are any questions.
No questions.
All right. Maybe one question that I had was, you consider some of these rules, right, logical. How many are you considering in these applications?
So there were a small set of hard constraints, mostly for the collisions, right, when we train them, and some number of soft constraints, but it is less than like 10, essentially.
Any other? Okay.
Thanks, very cool. I don't know if I missed something, but what is the interface that the pilot gets in real time? Because it was not shown in the video. So is there like a way to inspect the policy and to understand the kind of decisions?
Something that should be worked, in all our places, how much they should be aware of. There should be it should have a predictive component always, right? And especially if things start to go wrong, because you don't want to react, but you want to react to something that's predictive. And it's part of the user interfaces and all that. I think another challenge for all of us is the interface. Whatever we and I, us do, how we interface this with human experts and what they kind of see and what they kind of understand.
Thanks.
Any other questions? Okay. So in the spirit of having academia and industry session, the next speaker actually is from the government. And is Alvaro Velasquez. He's coming from the DARPA I2O office from FRL before DARPA, and a PhD from University of Central Florida.
Thank you, Alberto. Thank you, Dragos, and everyone for coming. So as you saw from the previous presentation, there was a DARPA logo on the aircraft. So the place where I work is where we like to fund these very cool things. We don't get our hands dirty ourselves, but we find good people like Dragos to actually do these things. So in the spirit of that, I want to ask a favor from this audience. As I present my talk, I want you to think about what are the areas where we should be investing in as funding agencies, and where the community should look at that the private sector is not incentivized to look at. Because we know the Googles of the world, we know the Metas of the world, the Amazons of the world, they have these huge budgets and they have these profit margins that they have to meet. We don't have these budgets, unfortunately, but we're also not constrained by having to make some kind of profit. So given that, where should we be in? And in particular, I want to talk about one area that I think is very exciting within Neural-Symbolic AI. Autonomy. Is the microphone? You can hear me okay? It cuts out and out. All right. It's Neural-Symbolic autonomy. And what I mean by autonomy here is, much like Drago said earlier, is this sequential decision making. It's your reinforcement learning, it's your planning systems. This is an area that is much more difficult than language and vision. So I'm going to go over a lot of the challenges. I'm going to go over some of the early work that's been done in this space. I do currently manage a Neural-Symbolic AI program called Answer, but I'm looking forward in the horizon as to what other investments we should be making. I think there are many programs we can come up with in this space, and so I appreciate your collaboration, perhaps in having some discussions on what those problem areas are. But to make sure I put it in a common language so we can all be talking about the same thing, when we talk about autonomy, we typically think of a decision process. Decision process is the formalism by which an agent interacts with an environment. It consists of a set of states, which are the operations that an agent can make, a set of actions that the agent can take in any given state. So for example, here, this is a deep racer simulation environment. It's a very simple 3D autonomous racing environment. The agent can observe the track. The action space is very simple. The agent can either throttle at 1 meter per second, 2 meters per second, steer at 15, 30 degrees. You have some transition dynamics that tell you if at time t I take an action, what should I observe at time t plus 1? And finally, you have a reward signal, which is basically the proxy for your objective. So if I'm trying to learn how to race very quickly, a very simple reward signal is to provide a small penalty for every action you take that doesn't lead to the finish line, and perhaps a huge reward for every action that leads to the finish line. And so what this does is it provides the agent a way by which it can label its experience through the reward. And once you have enough experience, you can find the underlying patterns that constitute a good decision-making policy. And that's all we really want to do. We want this policy that maps any given state to some action such that you are optimizing some reward. And this is a very simple abstraction, but of course we can add arbitrary complexity to this. The states could be partially observable, the transitions could be non-Markovian, you could have multiple agents, etc., etc. And we have seen some tremendous successes from the private sector here. And there's a reason why whenever you see these very sexy architectures in autonomy, like AlphaGo, AlphaStar, it's always from big tech. It's because it's very, very expensive to actually train these architectures. It can be on the order of hundreds of millions of dollars. And of course, we don't have these kinds of budgets. Just to illustrate what these technologies are, it began more or less 10 years ago with DeepMind. This was before they were acquired by Google, where they trained DeepQ networks to play Atari at a superhuman. This was followed by AlphaGo, which was used to defeat the world Go champion. This was a combination of planning and reinforcement learning, Monte Carlo tree search plus deep learning. This was followed by Thomas Sandholm's group at CMU with Liberatus, where they could be top poker players. Then OpenAI came along. They had OpenAI 5, which could be Dota players. And then you had AlphaStar. And then there's been a bunch more of these. But the problem here is, if you look at, beginning with AlphaGo, The amount of games you have to play just to match human performance is on the order of 10 million. Now, we don't know what a human would look like if they could play 10 million games of Go. So in some sense, this is a very unfair comparison. The total reported number here was something around 29 million games. And the associated power budgets just to train this architecture was over $10 million. This gets even worse as you go into more complex settings. This is OpenAI's 5 bot, where they collected 900 years worth of data every day for a total of 45,000 years worth of data. So extremely inefficient. And the worst culprit being AlphaStar, where they collected 60,000 years worth of data. And not only that, they required close to 1 million replays from the top humans, because of course a lot of people play StarCraft, so you actually do have readily available data to train these things. And if you didn't have that strong human prior, with all this data, you would fail miserably. With no human data, anybody in this room could beat AlphaStar. And so this raises some very serious concerns about the efficiency of autonomy. We already know that the machine learning architectures for vision and language are themselves somewhat data inefficient, but that compounds in the autonomy setting. So this is a very important problem to look at. And this is a place where in the last few years, the Neural-Symbolic AI community has made tremendous progress. In particular, when you bring in symbolic structures to define your reward signals, your cost functions, your transition dynamics, there's a lot of data efficiency to be gained here. However, data inefficiency is not the only problem. We also have the need for reliable AI. This is not a problem in vision and language, but in the case of autonomy, since we have to provide a reward signal by which the agent knows what is good or bad, this introduces a lot of vulnerabilities. For example, there's a quintessential example of the game of Mario. You want Mario to beat this map, right? What's a simple reward signal? If you win the game, you go all the way to the castle, you get some reward. So that kind of behavior is positively labeled to derive the patterns of winning the game. If you don't win the game, you get 0 reward. In principle, that's fine, but it's incredibly data inefficient. So if you were unbounded in resources, that would work, but in practice, we have to handcraft these reward signals. So what did people do? They said, okay, well, if we want Mario to beat this thing really quickly, we're gonna provide a small penalty the longer it takes Mario to beat the game. And in hindsight, Mario learns the obvious thing, which is to kill himself as quickly as possible so as to avoid that penalty. Now, I want you to consider if in this very simple game, this phenomenon can happen, imagine in a complex industry setting, what could happen? Again, this is an area where Neural-Symbolic AI can play a very large role. So for example, for those of you familiar with the reward machines literature, there are ways to take structured representations of objectives using temporal logics, using various kinds of automata, using formal languages, in a way that you can provably design a reward signal that won't lead to this kind of behavior. Finally, there's a need for, of course, safe AI. In fact, safety, I think, was the main property that was being looked at under Boeing's effort in assured autonomy. And it basically means avoid doing something disastrous. It applies heavily in the autonomous driving sector, where it is very easy to violate these properties. Here I've listed 2 different incidents where a safety property was violated from the symbolic side and then from the neural side as well. So first we have an incident with a Google self-driving car where there was an accident because, quote, the car assumed that the bus would yield when it attempted to merge traffic. So again, if you're in a very controlled environment, if you're in a simulation environment, this logic makes a lot of sense. But the real world is a lot messier than this. So it's easy to violate these kinds of properties. At the bottom, we have the unfortunate fatality in an autonomous driving incident where the Tesla vehicle mischaracterized the bed of a truck for a cloud and drove straight through the truck. Again, this is a violation, in this case, of the neural component of the system. And presumably, if we could cleverly integrate both of these modalities, it would lead to safer AI. For example, in the first case, it's very obvious that there was a flaw in the logic, but if you were to add a neural network to predict sentiment analysis, to see if the bus driver was distracted, a predictive modeling of the trajectory of the bus, whether it was likely to stop, all of these kinds of things could have improved the safety of that system. Speaking of that neural-symbolic integration, what we see a lot in the literature now is one of two directions. We either go from the symbolic to the neural, or we go from the neural to the symbolic. It's actually very hard to do the deeper problem of integrating both tightly. And so I'll get into what I mean by that. But starting with an example for the direction of going from symbols to neurons, we have a very interesting budding area of research known as differentiable logics. Conventionally, we wouldn't think of logic as differentiable. If I give you a Boolean formula, if I give you a linear temporal logic formula, whatever your favorite logic is, it's a very discrete structure. You wouldn't think of it as a smooth, continuous representation. But what if you could? What if you could smoothen these logics? What does that afford you? Well, what it does is that now you can take these autonomous agents, you can bring that differentiable loss, that differentiable objective into the loss function of the agent. What that does is it prevents the reward hacking that I explained with Mario, because these logics can provably derive correct policies that don't lead to reward hacking. And so people have actually done this for very powerful logics, even signal temporal logic, which has discrete continuous modalities over its variables, over its intervals, over its operators. Even that logic has now been made differentiable. On the other hand, we have the direction of going from neurons to symbols. So here, looking at the bottom effort, let's say you have a neural network. Of course, a neural network is kind of black boxy, it's very obscure. If you look at the learned parameters, you have no idea what's going on. But let's say we want to distill the knowledge of the neural network into some interpretable form that we can easily understand with some nice semantics. There's early work in this space from 2021 using something called quantified bottleneck insertion. And there's been a ton of different work along these same lines. The premise is very straightforward. You insert layers into your neural network, you quantize them, which means you train them in such a way as to remain binary. Whereas all the other layers are these floating point, messy numbers, you have these other layers that are binary, and whenever you collect experience from your neural network, you collect the activations of those binary layers, and a community like this should know what you can do with that. You can learn a formal language, because those binary vectors are the alphabet of some language that is capturing the dynamics of your neural network. And so this has been done to great success to derive finite state controllers from very large networks, to derive deterministic finite automata, to derive human readable explanations of behavior from what is otherwise a very large and complex black box. Now, that's all well and good. It's very impressive. It's a good starting point. But I think the deeper problem is to reason about both the neural and the symbolic simultaneously, as opposed to going in one direction. Why is that such a big problem? Because whereas it's easy to compare a symbolic representation to another, for example, we have graph distance metrics and all kinds of various metrics by which we compare symbolic structures. And we also have all kinds of nice metrics by which we compare neural structures, different manifolds. Imagine the question of instead comparing one neural symbolic representation consisting of both continuous and discrete components, like a manifold and a polytope, to another representation consisting of a manifold and a logic formula. It's not intuitive how one can actually embed these into the same space and be able to compare and reason about them. So I would say that's a very big open problem. But practically, we are seeing some very powerful architectures that implicitly do this to some extent. So if you look at the vision language modeling community, the text-to-image generation community, their architectures seem to entangle the semantics of language with the continuous representation of images in a very interesting way. In a way where you can prompt very, very complex queries and get very interesting results. And so I think we need to be able to leverage the success in those communities, the success that we see from vision language models. Can we replicate that for autonomy? The answer is currently not, so I want to get into the details of why these architectures are so successful for vision and language, but why they are currently not good enough for autonomy. And I think that is a whole line of funding and work that a community like this should be inspired to look into. It all begins with the Humble Transformer, 2016-2017. This is what almost every foundation model is based on. A foundation model is a large model that can generalize to many different tasks. So ChatGPT is the obvious example here. How do these foundation models work? They're mostly based on these attention networks that I just mentioned, and the attention networks themselves, not to oversimplify it, but they are pretty straightforward. It's a deep learning extension of database retrieval. So you might imagine that in a database, you have a set of values, you have a key associated with each value, and you have a query. You want to extract some value. You compare your query with every key. The key for which there is the strongest match, you retrieve the value. Attention networks come along and say, what if the queries, the keys, and the values were actually learnable embeddings themselves? Attention network. Now, bone of transformer architectures, but it is the most important component. Everything else is standard feed-forward neural networks, batch normalization, the standard machine learning stuff. Why is this not enough for reinforcement learning and for autonomy? This is something Jan yesterday. These architectures are autoregressive. You might recall from Jan LeCun's talk when he was talking about autoregressive architectures. They're very bad for actually making decisions. They're good for predicting the next token in a statistical manner, which works for language, because if your next token can be 1 out of 10,000 different words, that's actually not a huge dimensionality. But in the autonomy case, you're reasoning about a long-term objective. In the autonomy case, every action you take changes your future data distribution. It's a completely different problem. And so the problem of developing the right kind of architecture to enable a foundation model for autonomy is very much an open problem. It's very much an important problem. But let's say we figured it out. Let's say we have the architecture. We know exactly what it should look like for sequential decision-making, for autonomy. Now we have an additional problem. How do we actually train that architecture? In the case of language, we have a huge underlying assumption. There's a reason why LLMs are so successful. It's because even though you're training over very diverse text, Wikipedia, like books, exams, there is a shared syntax and semantics of language. And so for those of you familiar with the technical underpinnings of machine learning, we usually make this thing called the manifold hypothesis. When we're trying to learn something, even if it's very high dimensional, we assume that there exists a low dimensional manifold that we're trying to extract. Language has that to some extent. It's your syntax, it's your semantics. What does that look like for autonomy? Because if we have a diverse set of different simulations or games or real-world tasks, the states look different, the actions look different, the transitions look different, the rewards look different. So do we have that shared semantic, syntactic structure? We don't know. This is an open question. But it seems to be a requirement to enable the kind of training and the kind of generalization that we see for language and vision. Again, in language, if you can take all the text you want, delete every 10th word, and learn to predict it. It's as easy as that. In autonomy, we don't have this. But let's say we do. Let's say we have the architecture. Let's say we have the methods by which we can train them in a self-supervised manner. We have an additional problem now. How do we fine-tune to a downstream task? If I give you this beautiful, powerful foundation model for autonomy, and you have a very specific task you want to solve, how do you fine-tune it? Again, we have a disparity in states, actions, transitions, and rewards. But that is what we would like to get to. We would like to get to a place where we can take arbitrary games and simulations from the internet, like LLMs do. We can leverage the semantic shared structure of these simulation environments, and we can train a foundation model that can interact with the world and receive feedback and generalize from that feedback. And I think the way we do that, as I've been alluding to, is by figuring out what those shared abstractions are that LLMs sort of take for granted. Here I have a very sort of trivial illustrative example. We have two very different environments here. We have mini-grid, which is a super simple grid world environment, and we have a real world, hospital environment. We have some robot running around. It has to open doors and inspect the rooms, situational awareness type of autonomy. Let's say it's useful for this agent to know what a door is. They should learn to detect a door, interact with it, and so on. Conventional machine learning wisdom would say, well, we're going to look at environment A, we're going to collect a bunch of pictures of doors, different angles, different lighting conditions. We're going to learn visually what a door is, and then we'll transfer that over to environment B. Clearly, in this context, that conventional wisdom goes out the window. Because in mini-grid, a door is simply a yellow square. You interact with it, it turns into a yellow line. In this other environment, you have a real-life door. So visually, these are two completely different things, but they share an abstract semantics. A door is simply a movable barrier housed inside a larger non-movable barrier, which is your wall, such that when you interact with it, you go into a new area. What does that mean? That means we can now ground the shared semantics over different environments in an unconventional way. We can learn what is movable, non-movable through interactions with the environment. We can learn what it means to move into a new area by, from an information theory perspective, observing a high amount of entropy in our predictive model. And so now we have a very interesting way by which we can share information across very different environments. Moreover, this could be a much more robust representation. Because imagine what a conventional representation of doors looks like in machine learning. You train a door detector, there are all kinds of attacks to full door detectors, right? There are imperceptible attacks where two doors look identical and then one gets misclassified as something else. Here you would have to find a door that meets all these criteria such that it is not a door, which is much harder to do. And here to shamelessly cite some of my own work, we have looked at this from the rewards perspective. If you have a shared abstraction of the reward signal between different environments, there's actually a lot you can do with that abstraction. And there is a great deal of disparities that you can be robust to in terms of your states, your actions, and your transitions. For example, if you represent your reward as a deterministic finite automaton, the individual subcomponents of the automaton now enable you to decompose the problem into smaller problems, thereby improving data efficiency. The fact that this is a formal logic allows you to prove that the reward signal you come up with will not lead to the reward hacking we saw with Mario. This allows you to also distill symbolic knowledge into conventionally non-symbolic structures, like the loss function of an agent. So that there are a lot of interesting one can do by looking at these shared abstractions. But we only looked at it really from the perspective of rewards. To really tackle the full problem of foundation models for neural-symbolic autonomy, we need the shared semantic abstractions for all the components that make up a decision process. So at the very least, your states, your actions, your transitions, your rewards. This is an area that I'm committed to in my own personal research. But what I want to ask all of you is more broadly, not just within neural-symbolic autonomy, but just broadly neural-symbolic AI, what it is that you think we should be investing in, that the private sector is not properly incentivized to look at. So I'll end it with that question. Thank you very much.
That is not working.
That's not working.
Thank you, Alvaro. Is there? Okay.
So great talk, thank you. So I'm just trying to react to your question. I mean, I have this feeling that with Neural-Symbolic we'll be able to learn even more powerful machines and so on. However, the big limitation that I see in deployment is assurance. So we've been building increasingly powerful machines that we're not quite sure what they do, and we struggle to deploy. And unless we have the budgets of Waymo to test for 10 years, 24/7, we're going to struggle to deploy. So what are your thoughts on assurance, on verification, on safety, and how we make that happen?
From a practical perspective, my thoughts are a little bit boring. So you mentioned Waymo, and it's interesting what Waymo does. They have at least 20 billion miles simulated and at least 10 million real-world miles driven. But what's interesting is that they don't use those miles to train an autonomous agent per se. They use those miles to train predictive models of pedestrians, predictive models of cars, so that then, given those predictive models, they use classical methods like control theory. So I think that from a practical sense, I think we have to defer to the classical methods now. But from a more fundamental sense, for the fundamental research where we can perhaps take more risks, I would be very curious to see a tighter integration of formal logics and deep learning. We're seeing some work there, but if you look at the verification of neural networks community, we're still very much limited. We're still very much dealing mostly with ReLU activation functions. We're still very much struggling to handle other components of deep learning like average pooling. Simple things like this, we really struggle with. So I think there are big leaps that have to be made in the verification of neural networks community. Yeah.
I have a question. You're talking about this fundamental for autonomy, which is very similar to what Jan LeCun, in some sense, was talking about. But I'm wondering, you know, in robotics and autonomy, we have spent a lot of time to try to generate these, actually are symbolic representation in many ways. And the most important reason why that has been done is because we want to be able to capture uncertainty and propagate uncertainty. And these foundation models are really, really powerful, but because they have this really obscure, right, representation, they build obscure representation, becomes extremely difficult to be able, you know, to consider uncertainty, right? You can ask ChatGPT anything you want, and it will give you whatever it thinks is the right answer with 100% confidence. So how do you envision this sort of, you know, trying to leverage what has been done on this more expressive, symbolic representation in some sense, or explicit representation better, compared to a foundation model for autonomy?
So it's interesting because we do have these symbolic abstractions that generalize across different environments, but we typically make an assumption. For example, in the sim-to-real transfer learning literature, you'll assume that they share some dynamics, typically some differential equations models and things like that. But you make your simulation environments very high fidelity, which is to say that to the extent that you have multiple simulation environments, they all look very similar. I think there's a counterintuitive claim here that we should make them look very different, actually. Because overfitting is a big problem in machine learning writ large, but in autonomy in particular. Agents can overfit to a very specific sequence of actions, and that can have all kinds of vulnerabilities. So my argument would be leverage the shared symbolic abstractions we have now, but make your environments very different. Like the example I show, mini-grid to the real world, there's a healthy level of noise that you need to get machine learning systems to generalize. That's been known for a very long time. So I think that's the direction we have to go in, is to insert the right kind of noise, leverage the current abstractions we have, and come up with new methods by which we refine those abstractions based on their violations, right? If the agent acts in the environment and then it violates it, this is a counterexample. Counterexamples are very useful for then refining the abstractions. So I think that's the direction to look at. Now you brought up large language models. Of course, that's a very big problem, how you verify these things. But there is some early work on symbolic distillation. How do you derive a knowledge base, a symbolic knowledge base from a language model? What's good about that is if you have the symbolic representation of a language model, you can detect things like contradictions. And with contradictions, you now have counterexamples by which to fine-tune the language model. So I actually have a paper this year, if you're interested, that was published in that in International Conference on Assured Autonomy. So I'm happy to share that.
Thank you so much, Alvaro. Any other questions? Since we started a little bit late, we actually are catching up. So do you want to present the next? Okay. Okay, we can go to the next talk. So the next talk is presented by Kuvun Ho Engen. Sorry, butchering your name. So the title of the presentation is Closing the Neural-Symbolic Cycle, Knowledge Extraction, User Intervention, and Distillation from CNN.
Hi, I'm Kwon. I'm presenting my poster as in a presentation form. So the topic is closing the neural-symbolic cycle. And in this cycle, I'm trying to extract knowledge and hopefully using those knowledge to intervene with a domain expert and hopefully getting feedback from the domain experts. And ultimately, trying to find a way to learn from this knowledge itself. So it's a team of people, and it's a collaboration with city and university and Fujitsu Research. So let's begin with the problem statement. So basically, I'm starting with a very simple problem, which is a CNN, which is generally used for doing predictions in imagery data. They are very good. But then the problem in terms of interpretation and transparencies, they're lacking there. So when we put this into a critical domain, for example, medical use, it faces a lot of challenges, not just to gain the technical performance, but also the trust and the adaptabilities and the deployments within the actual hospitals or medical scenarios. So the goal here, I've set it 3 in a sense that the first thing is that the model has to be more interpretable and potentially more explainable not only to the AI community where these models are developed, but more explainable to the people who are actually using it. And in the medical domain, that will be the doctors, for example. And maybe when it goes to the regulatories, it can also go into the regulatory bodies and hopefully gain the trust. And with the knowledge, hopefully the communication linkage can be strengthened. So if we are able to communicate the knowledge, hopefully we can get more feedbacks also from the humans. And in such a case, I'm also trying to find a way whereby we can encapsulate this knowledge back into a better model or more presentable model that hopefully it will be more transparent and also more deployable in the sense. So to achieve this, I've built a proof of concept. So this is the only medical slides that I have, so bear with me. And I've built a binary classifier to detect a lung disease called plurifusion. So by definition, plurifusion is just the accumulation of fluids when you have an infection. So you will see at the red circle where you have the whiteness patches. That's where the fluids is accumulating because of gravities and that liquids is there. So it can be caused by different diseases and associated symptoms like from pneumonia and heart failures. So hopefully by making the model interpretable, we can maybe understand if there's any linkage and vice versa. Oops, it keeps jumping. But so for those who have seen my poster, this is the cycles I presented. And I'll just briefly go through what it is. So at the very beginning, I have a very black box model where you just throw in a bunch of images into a CNN model. You provide a output and with good accuracies and performance. But then, of course, as I was mentioning earlier on, this is very uninterpretable. If you give it to the doctors, you can't communicate with them. So I try to extract the knowledge, and for each of these steps, I'll explain in more details in the subsequent slides, but let's go through these cycles once more quickly. Is that I will extract some knowledge and do a lot of analysis, and hopefully associate this knowledge into more relevant to the clinical features. So trying to associate some of the features that you might have extracted from a CNN into more clinically relevant ones. Then we will be able to generate some symbolic rules. And in this case, I'm doing it in a simple decision tree where it will give you an idea of some symbols. But for example, you will never know what ET is or PA as a symbol. So this analysis basically trying to correlate things such that ET will mean something more clinically, where in here you will see that the heart from healthy, which is green, to unhealthy, which is red, and you can obviously see the visual differences. And this is the way I'm trying to translate symbols into more relevant concepts. And this, from the look of this is also more closer to how a doctor will visualize a medical image. So we will be able to provide a better description of how this rule sets is. And so we present this to a doctor in a user interface. And I think we have many talks about human in the loops, and I also agree that there's always a point where a human can check, validate, and interact. I think the interaction is very important, such that maybe, as we all know, CNN not only extract what things you want them to extract, but there are also other things from the background, from many things that may also be included. So this is also a point where the doctor can look into all this information to see if some of the symbols here are really representative clinically, and they can also make suggestions to say, hey, maybe there's a better way, so that we can use these kernels as symbols to form a more relevant tree. And I consider that to be improving the relevancy in terms of clinically. And from here, at the moment, I'm really interested to see how we can learn from the knowledge itself. So at the moment, I'm just simply using a teacher and student network to basically encapsulate how a retrained network can adapt and respond correspondingly from the adjustment. So to begin with, when I try to conduct the analysis to associate with the features, well, first of all, I need to quantize them and basically creating those activation maps into a certain data points, such that I can identify how it changes with certain change in the activation map. So these are some of the equations. Basically, you have an activation map for an image for a specific kernel at the last layer of a convolution network. And you use, for this example, I use an L1 norm to create a number. And also, I can also create a threshold based on the mean and to binarize them to create a decision tree. But these data points also leads to a secondary exercise that I have done, is to basically not just putting numbers to a kernel, but rather what exactly these numbers corresponding to. So basically, I try to compare the L1 norm values with radiomic features to find some correlations, and of course also just to visualize what exactly they are, to create that association clinically, and to provide that descriptions. And of course, there's the interaction. So I can't just throw them the code or whatever. So I built a very simple interactive interface where the doctors can basically manipulate the drop-down menus of different kernels. You can evaluate what these kernels are corresponding to. Maybe some are corresponding to a certain regions. Maybe some are not interpretable, so they can discard them. They can also hover around to see whether some of the suggested reasonings are right, so they can do that checking. And of course, for specific images, they can also try to see if a certain rule here makes sense, and if not, trying to adjust it. Then this is the beginning where I'm really trying to learn how to learn from the knowledge itself. So this is just a very vanilla version of the teacher and student network, where the teacher is where the source of learning is, and you try to adapt a new model where you basically learn the response for now. So there's the distillation loss for learning from the teacher. And also there's a corresponding measure of student loss that I've also evaluate along. This is not part of the constraint for training, but rather a corresponding change that I'm trying to observe and see how close it is to the ground truth. So what I've seen here is that if I use all the kernels, I will be able to really learn something along the way. And if I really reduce the amount of information to only just those interpretable kernels from different regions, again, I will learn something. That's for sure. And in fact, even reduce further on where the doctors say certain regions are more important, I still learn something against the teacher. That's the way how the constraint guides the learning. And last but not least, I've put in, where's my cursor? A case where basically these are irrelevant kernels where you have the collarbones, which is not relevant to the accumulation of fluids. And this graph will just show that you learn something. But the next graph, the student loss, is how close it is to the ground truth. And what I've observed is that it will only decline when you provide relevant information, but you still go flat if you provide only irrelevant information. And of course, that will basically directly translate to the accuracy and the performance and so forth. So in a way, it also checks that the information that I provide are relevant to the target prediction. So just another example, basically, is now I fit into the clinical relevant tree, or for example, just a single kernel that is relevant for the upper mediastinum or the cardiac ciliate. Again, for distillation loss, you basically have a really quick learning to build that association between the information, the features to the target output. But if I put one that is really not specified, really random, then it's really hard to learn it to start with. And also you will see that it will never only for the yellow ones, which is uninterpretable or unspecific, that you will never learn to get close to the ground truth. So these are just some of the examples I started to learn about how we can capture the knowledge and hopefully to build that next version of models to be more appropriate to the information. So to conclude, is that this is an overview of a framework where I hope to capture the knowledge and hopefully through the use of symbolic systems to build up the communication and ultimately how we can translate the symbolic and all the knowledge from there back into a better model. So if we can manage to complete this task, I'm hoping that this will be a more traceable way of how knowledge transfer between different systems and back in order to build up that trust of what actually is being learned in a model before it deploys. And future work is basically, as I was mentioning, to enhance that learning that I really want to appreciate. And also not only from a single source of knowledge, but multiple sources or maybe multiple modalities. And eventually, how we can express human-based literally directly from humans, the doctors, and to represent it. And so this is basically how we can add new knowledge, how we can improve. It might not be a teacher and student network, but how can we improve that learning algorithm and ultimately a better tree to combine all these informations together for a better explanation. And that is the end of my talk. And thank you.
Any questions? Questions? All right, yes.
Maybe one question. Have you tried with some expert human to understand the traceability that you're talking about?
That is a very good question and very expensive question because getting a panel of doctors in this case can be very expensive. So there's these baby steps that I'm building on. So we, in the team, we collaborate with a doctor and at least we start getting into that process of improving the performance for getting the feedback on. And I believe in previous talks that there is human analysis and evaluation. And that is one of the to-do tasks to make sure that that part of the components is important, well, done right. Yeah.
Any other questions? All right, let's thank our speaker once again. Thank you. Right. Next talk is by Mihaela Stoyan, Emanuela Gengilia, and Tomas Lukacevic.
Thank you. Hi everyone, I'm Mihaela, and I'll present our paper titled Exploiting Tenors for Deep Learning in Autonomous Driving. Neural networks are powerful tools, however, they are still black boxes which can output unpredictable results in different circumstances. And this becomes especially important in safety critical scenarios, such is the case for autonomous driving. So now to have a look at what could happen in a real world setting, here we have an example of an actual prediction we encountered while working with state-of-the-art neural networks. Here we have a neural network that receives as input a sequence of frames, and its goal is to output bounding boxes and associated sets of labels. And as we can see, the model decided to output that the traffic light is both red and green at the same time, when in fact it was just red. So then it becomes very easy to see that deploying such models in practice might not be a good idea and could very easily lead to accidents. For example, in this case, the self-driving vehicle might not have stopped at all at the red traffic light. So having purely data-driven models decide how self-driving vehicles should behave might not be enough. And instead, we could use neural-symbolic methods to make our predictions safer by discouraging the outputs that violate the background knowledge we have. And for example, the background knowledge could be expressed as logical constraints and, or rules, and these rules are usually easy to obtain and can capture common sense facts such as that a traffic light cannot be both red and green at the same time. Having said that, we designed this whole work around the autonomous driving dataset called RODAR. This is a recently published dataset. And the reason for this is that RODAR is the only dataset that fit our scenario, namely a real-world setting, with a relatively large number of logical requirements. RODAR is based on the road dataset, which contains 22 videos of about 8 minutes long each, and it also has labeled bounding boxes, as we can see in the example on the left. Additionally, RODAR contains 243 logical constraints that have been manually annotated. And some examples of these constraints include a vehicle lane cannot be a parking lot, or if something is crossing, it is either a pedestrian or a cyclist. Our task that we considered for this real-world setting was the event detection task, which simply assumes that the neural network receives as input a sequence of frames. And the goal of the neural network is then to output bounding boxes along with a set of labels that characterize the agent, the action of the agent, and the location of the agent for each bounding box. And for example, we have on the left a pedestrian here that is moving away from the self-driving vehicle and is on the left pavement. So we have the RODAR constraints that have been written for the event detection task, and now we wanted to inject these rules, these constraints, into our neural model. For this, we used a popular approach, which is to constrain the loss using T-norms. And one thing we have to keep in mind when working with such methods is that we cannot use directly the hard constraints as we had them here, because this would break the differentiable nature of the model. So instead, such methods typically relax the hard constraints by using transforms such as T-norms or T-conorms, depending on whether we have conjunctions or disjunctions, respectively. And such transforms, such as T-norms, are applied on real values, as the lowercase letters here, which represent, for example, can represent, for example, the output of neural networks, and are directly mapped to labels from our original hard constraints. Additionally, the T-norms can come into different types. For example, they can be Gödel T-norms, which simply take the mean between the real values, or we can have the product T-norms, which multiply the real values. But regardless of the type of the T-norm, we can always think of the result of the T-norm as being an indicator for the degree of constraint satisfaction, given the neural network's output. So then it becomes straightforward to see how we can use the result of the T-norms to a regularization term in the loss to be backpropagated. Okay, so why is this a complex scenario? And why does it even matter when constraining the loss using these popular T-norm-based approaches? So we have seen that RODAR contains 243 logical constraints, which are written over 41 labels. But the actual bottleneck and the actual obstacle for the t-norm-based loss here is the number of anchor boxes that the detectors output during the training. So this number actually accounts for about 8,000 anchor boxes, and the anchor boxes are something like the rectangles that you see here on the left, but this is for inference and not for training, so we have fewer. What this means is that the standard t-norm-based losses would actually require working with 3D matrices containing around 80 million elements per frame at each step of the training. Now, so given this, we can actually think of the bottleneck of standard implementation being that the t-norms may have very high memory requirements, and they may even be able to apply in complex scenarios. So for this reason, we became interested in the problem, and we eventually showed that it is possible to define memory-efficient t-norm-based losses that can work for complex tasks such as event detection in autonomous driving. And before we go into the details of our method, let's just have a look at memory assessment, a memory comparison between the standard implementation and our approach. So in the plot, on the right, we can see in purple the standard method, the standard implementation, which can only cover 40 constraints at most. Remember that we had 243 constraints in RODAR, so 40 constraints is not even a quarter of what we needed. And we also used a pretty good GPU, which had around 24 gigabyte memory. So on the other hand, we see our method in green that can actually be used to compute the t-norm-based losses without sampling anything, keeping all the information there. So how did we design our approach? We started from a crucial observation. And this was that the constraints in the real world are written over a very small subset of the total, of the set of available labels. So then we could just throw away the dense matrices, we didn't need them anymore, and we could use sparse matrices instead. To see how this works, assume we have a set of constraints, such as here in the blue box, and we also have a prediction matrix P, which contains in its columns the label scores, and in its rows, we have the numbers corresponding to bounding boxes in a frame or perhaps in a batch of frames, depending on the user's choice. The goal is then to compute the degree of satisfaction for each constraint and for each prediction, so for each bounding box. This fortunately can be expressed as a matrix G in a compact way. So how do we compute this goal matrix G? We used an iterative approach. But first we started with the matrix G instantiated to the identity element of the disjunction. So then for the process, for each label, we first determined the constraint in which that label appeared. Then we update the columns of G, which corresponded to only the selected constraints, rather than updating all columns of G. So what exactly are these updates that I'm talking about? They are simply t-norms of the selected constraints at each such iteration that are applied on the predictions made for the current label. So perhaps the easiest way to explain this is with a simple example. So here we have a case where our set of labels contains just 3 labels, car, moving, and stopped. We also have a prediction matrix containing predictions for 2 bounding boxes, in this case coming from different frames. And we also have a set of just 2 constraints. Now, if we look at the constraints, and if we look at the prediction matrix, what we'll see immediately is that the first prediction violates the second constraint. This is because the model predicted that the car is both moving and stopped at the same time. So how can we capture this violation and use it in the loss objective? So our process involves this iterative approach, which means that we start with the first label here in our set, which is car, and check where it appears. In this case, it just appears in the first constraint. So we'll only have to update the first column of G rather than all of its columns. And it turns out when we scale this up, it makes a big difference, as we have seen in the memory assessment plot. So in this case, we use the Gödel-Tycho norm, and this is simply because we have our constraints written as disjunctions. For this, we apply the maximum, so the Gödel-Tycho norm in this case, the maximum over the original values in the first column of G, which was instantiated to 0, and the prediction made by the neural network for label car. Therefore, we get our first update in the first column of G. Moving on, we go to the second label, in this case, moving, and we check where it appears. In this case, we can see it appears in both constraints, which accounts for all of the constraints we have. So we'll have to update all of the columns of G. Now, this is a very rare case in the real world. You very rarely have to update all of the columns of G, because it wouldn't really be the case that you'll have one label appearing in all of your constraints. So the main difference then is that this label appears negatively, whereas car before positive. So we'll have to subtract the actual predictions made by the neural network from 1. And then again, we apply this on all the columns, and we get our updated matrix. Finally, we reach our last label, which is stopped. Again, this appears negatively, and we subtract the original neural network prediction from 1 for this reason. And since it appears only in the second column, we only have to update, it appears in the second constraint. So we'll have to update only the second column of G rather than all of its columns. So we have seen previously that the first prediction here violates the second constraint. Now, this is indeed reflected in the matrix we have just computed, which indicates the degree of constraint satisfaction. So for each prediction, which appears in each row, we have a constraint satisfaction score for each constraint. Now, we see that the row, so the first prediction, has a very low score in the second column, which is exactly what we expected. Moving on to the experimental analysis. First of all, we have seen that with our method, we can actually use the t-norm-based loss for a complex scenario such as event detection for autonomous driving. Secondly, as we expected from prior works that used constraint loss approaches, the results are improved, especially when using limited amounts of labeled data. In this case, we can see we got the highest improvement using the Gödel-Tycho norm. Now, the second advantage of such methods is that using unlabeled data usually helps. Fortunately, it's very easy to obtain unlabeled data for autonomous driving. We just need RGB images captured from the perspective of the driving car. So we applied our method on both labeled and unlabeled data. What we have seen in the beginning is that there wasn't quite an obvious trend whether unlabeled data helps, but when we introduced a warm-up period, we actually got improvements for all the t-norms. What warm-up means is just that we applied the t-norm-based loss a bit later in the training on the unlabeled data rather than right at the beginning. And this saves us time, first of all. And secondly, it also decreases the chances of getting faulty losses. Having said that, we have seen a lot of interest in the topic of deep learning with logical constraints over the past few years. However, we would like to see more researchers getting interested in the real-world applications. And for this reason, we are organizing the RODAR Challenge, as Eleonora mentioned on Monday. And yeah, if you are interested in the details, please visit our official website for the challenge. To conclude, we showed that standard implementations of T-norm-based losses fail to scale. And for this, we formalized an approach for computing a memory-efficient T-norm-based loss. To put our work in the bigger picture, this is just a small step towards a more general direction of having models that consider background knowledge when making their decisions, which we hope will become an actual requirement when developing safety-critical systems, especially for autonomous driving. This is all. Thank you for your attention.
Are any questions? So in this data set, you mentioned that the case where you had two constraints where you had to update. In general, did you see more than that, or is typically just two that happens? And what is your expectation in other contexts? Do you see that sparsity sort of disappearing at some point, or?
Thank you. I think the general observation is that in general we can rely on the sparsity assumption in the sense that we will have in the real world case constraints written over just a few labels. So in our case we have of course propositional constraints which are a bit simpler than what we could have otherwise. However, I still think that this would generalize further on perhaps other applications. So yes, I think the sparsity property will still hold on other use cases.
Any other questions? Yes, there's one there.
So T-norms, and if I'm getting this right, I think T-norms and fuzzy logic are AND, right? And correspond to AND, the connective AND. Can you only express constraints using AND this way, or if you take other fuzzy logic operators as your loss function, does that like generalize that way, or? Oh.
Very inefficient. Thank you. So yes, you could encode other types of constraints as well. Typically use De Morgan's law to convert from one to the other. Yes.
All right, any other final question? No.
Let's thank our speaker once again. Thank you. Our next speaker is Alberto Speranzon from Lockheed Martin. He's the chief scientist in autonomy.
Thank you, Dargash. So yeah, we have a coffee soon, so I'll try to be brief. So I was thinking to speak about some of the challenges that we are facing in trying to apply Neural-Symbolic to autonomy. And so the starting point is this picture that Dragos already showed. And if you look at the elements, they resemble very much what Jan LeCun mentioned. So that's typically how you think about autonomous system. You have a way to observe the environment. Typically, you build what Jan LeCun called a world model, which is the orient part. And then based on that information, you make decisions. And then finally, you make actions in the real world, which in the end changes the environment and you repeat. Now, generally, there are many different type of representation that you use. And I would say in robotics, in autonomous system, there is quite a bit of a mix of data-driven approaches as well as highly symbolic approaches. So especially since many of the sensors that this autonomous system use are camera, LiDARs, and so on. With all the advances in machine learning, of course, now many of the key components in the observe, orient part are deep networks, but you find them also in reinforcement learning as an approximation of Q function and whatnot. Maybe less in the action side, so you probably don't want to substitute a flight control system with a deep network. But in principle, you could think about neural-based controllers. So one thing that, in this talk I will speak, I tend to think about these blocks, as I showed to you, quite separate, so as different functions, compared to maybe, other approaches which try to blur the lines and maybe have a completely neural representation of the OODA loop, for the simple reason that ultimately we build systems that we need to be able to certify and understand when they may fail and do something about it. And so having a representation that is completely enclosed in a box like a neural network, maybe even a Neural-Symbolic network, but still where there is a highly, there are many components that are neural, becomes very, very difficult. So the idea is to take advantage of the modularity of the problem and combine neural and symbolic approaches in a more pragmatic fashion. The other problem is that if you want to build something that is completely neural, you will need a lot of data. There is a question of how do you collect that data. So that is one thing that, for example, distinguished companies like Boeing or Lockheed is that we cannot go around with these huge airplanes and just go and collect data about all possible situations in the world compared to what Google may be able to do by just mining the web. And the other problem is that simulation may be your best next option, but simulation have problems and so on. And of course, as Dragos mentioned before or showed in the video, you want to close the loop with humans. So autonomy is never in our mind something that it just goes by itself. You always have a human in the loop, and so then the more neural components you have, the more complex is to understand what's going on. So with that said, this is my thinking about the OODA loop, where you have neural and symbolic components or representation across all the different blocks. And one way to ground this problem is a project that we're doing with NVIDIA and some of the firefighter organization in California and Colorado about using multiple agents, multiple, could be flying vehicles as well, ground vehicle to contain wildfires. So the idea here is that you have multiple autonomous systems that are detecting where the fire fronts are, where it is moving, but it's more complicated than that because you also need to consider, for example, the type of terrain, what kind of material there is, is it flammable, is easier, has been dry for the last period, and so on. So there is a lot of complication on that side. But I think where the neural-symbolic side, the symbolic especially side comes very important is that you don't want this autonomous system to be designed exclusively based on this input like fires and the wind direction. Firefighters use very specific procedures. And if you want a good coordination between human and machines, you want machines to respect and follow similar guidelines. And so there is a huge amount of knowledge in manuals on how humans fight fires. And you want to be able to encode and constrain the autonomous system to follow those one. And in terms of decision, of course, is not only about observing the world. I mean, that seems to be the obvious thing. I have a network of agents that is able to gather a lot of data very quickly in a very large spatial environment. But it's not just for observation. You can actually use them to decide to preemptively deploy retardants in certain part of the environment, maybe even to light control fires in some other parts. So a pretty complicated problem. And so getting into some of the challenges that we are facing as we are trying to bring more symbolic knowledge or symbolic representation. So on one side, as I mentioned, one of very appealing capability that Neural-Symbolic provides is this idea that you can take symbolic knowledge and use it to constrain the learning, like we just saw in one of the previous talks. The issue is that I'm facing is this problem. Do I go out sometime to take more data, better data, or do I instead spend more time to develop a good ontology? especially in problems like firefighting, where there is not such an ontology already built. There is a question of what is the right trade-off. And I think that is one important challenge, because collecting data is very expensive, but also developing good ontologies, knowledge graphs is very expensive. And so what is the best trade-off? So that is one thing that we're facing. In practice, you can define certain concepts and try to derive other concepts from these concepts, or I could say, well, this concept is sort of my atomic concept, and I do not try to explain it or define it with respect to other concepts. I just go and collect data, and I use a neural network to learn what that concept is just from data. The other thing is that, as we are trying to incorporate this kind of knowledge, logical knowledge, into neural-symbolic architecture, there is this question of, are the principles that have been used so far to develop ontology and knowledge graphs still suitable for neurosymbolic method, right? All the literature on ontologies and knowledge graph has been created when there was the first wave of AI, if you will, right? And it was supposed to be used for different purposes. And now we would like to introduce or take an advantage of it for neurosymbolic approaches. Now, of course, if you have already ontology ready, obviously you would like to reuse them, but you don't want to recreate it. But if you have new problems, is the way and the principle that we use to capture knowledge still suitable if I want them to be part of a constraint, to constrain the learning? And so that is another question that I think as a community we need to think a little bit more about, is how do we capture knowledge if we want to use it for neurosymbolic approaches? I mean, capturing knowledge is one of those things that whenever you present to people that come from the very data-driven community, they say, oh, it takes too much time, it's very difficult, it's very ill-defined, how to capture knowledge in some sense. Labeling data is easier, but maybe the way that we need to capture knowledge is not this very complex as we wanted to do when we were thinking about this different purpose. And then the other question is, how do we integrate in different parts of the LUDA loop? In some cases, is constraint more coming from the logical constraint, like for example, that a traffic light cannot be both green and red, so it's something more at the perception and the orient side. But sometimes decisions about safety and so on, they're more at the decision making. Should there be a different way of capturing and representing this knowledge? One thing that, as everybody is exploring the possibility of using multimodal large language models to help on defining and automate or semi-automate the generation of ontologies and knowledge graphs. However, there is at least right now, this big question mark if developing the query the query engineering, if it is more complex than just developing the knowledge itself. In some initial example that we have done with some colleagues from MIT hasn't provided really very strong evidences that a large language model can really help a lot in defining a good ontology. So there is obviously this question of all these logical constraint, how do we combine it? The other part, and this is something that Alvaro mentioned, is about abstractions. So one obviously appealing idea about symbolic representation is that they enable you to go from super highly dimensional spaces to this very, very compressed domain that are symbolic. But of course, you want this representation to be, having some nice properties. So you would like them to be composable, of course, reusable and transferable. That is one thing that, for example, Alvaro mentioned, where you have, this grid world representation on one side, and then you have the complicated 3D world that we live in. How do you connect and transfer from one to another? Of course, interpretability is a key because we're designing things that human needs to use. And then, as I mentioned, the appeal because we have this compression and reduction. So there is a question of how do we develop these abstractions that are consistent. So in practice, what you would like is that if I am talking about the car at the perception level, so at the orient part, right, I build a world model about the car. And then at the act side, I would like to avoid the car. The concept of car needs to be consistent across the entire OODA loop. And so the perception abstractions, the world model abstraction, and the planning abstraction need to be consistent if I want to use symbolic representations. And especially if you want to be more reusable, then of course, if you do not have consistency, you're going to have big, big problems. The other part is, and this is very close to my heart about composability, I believe that is a key enabler for autonomy is to design systems that are highly, highly composable. Symbolic representation, of course, provide some of that. But is a question that I still have is about, do you need to engineer for composability, or is composability just a emergent property by the fact that you're using symbolic representation? So it feels like that if you are very much in the, for you, symbolic representation is more in the language. Composability kind of comes for free because language is composable, but if you use other kind of symbolic representation, unless you build in composability, well, then you are not going to have composability. So the question then becomes, as we are building abstractions, neurosymbolic abstractions, how do we engineer composability? Do we get it for free? And if so, how do we exploit it? And then there is, of course, again, the interpretability of the representations. One thing that sort of Alvaro touched upon a little bit is about the fact that ultimately these systems need to act in the world. So the fact that you're able to develop a symbolic or neurosymbolic abstraction, let's say that you are able to engineer it to be composable, is not sufficient because an autonomous system is not just living at a symbolic level. And that is one of the key things. So if you do vision with symbolic representation or language, usually what you do is that you go from pixel to symbolic representation, and then you do reasoning at the symbolic representation, and you are done. The problem with autonomous system is that the autonomous system does not live in the symbolic world. It lives in the 3D world or even higher dimensions. So even though you create a symbolic representation, you still need to go back into the concrete world to be able to do the act part, the decision and the act. So there is this problem of how do you manage the uncertainty and ambiguity. And here I'm talking about uncertainty and ambiguity from a slightly different perspective. It's not the uncertainty that you can have on a sensor. Oh, is that a car or not? I have a certain probability, or I maybe have multiple hypotheses, and so there is ambiguity. This is assume that your world is perfect. I have perfect sensor and so on. The fact that you go from a n-dimensional vector space to a set of symbols and relations, you are compressing the data, right? There is a projection that is happening in this direction. And so no matter what, you will have quantization noise, so uncertainty, and you will have multiple continuous states being compressed to the same symbol. So you will have ambiguity in the sense that if I want to go back from now the discrete symbol back to the concrete world, there will be many, many concrete states that are associated to the same symbol. And so now you have ambiguity, right? If I say I'm in front of the door with a robot, yeah, that's great, I'm in front of the door, but if now I need to take a handle to open the door, it may be very important to know if I'm few centimeters on this side or few centimeters of that side. And so you need to manage that ambiguity that is naturally happening because you're going up. But it will, you will pay a price going down. And that is one thing I think that is very, very interesting, right? So for example, it's, Alvaro was talking about the grid world and the real world. You have this semantic, commonality between the two worlds, despite the fact that in real, the concrete world, the representation are very, very different. But the question is that, as you are trying to create this symbolic representation, because they're lossy, what is the trade-off? What structure do I want to preserve as I go from an n-dimensional vector space to an alphabet of symbol and relations? And so that is very, very interesting, right? Because it's obvious that it cannot be just arbitrary. It needs to be very well thought if you want to be able to go back. And so, so this is, in planning, is the abstraction and refinement. You want this to commute. So that is another, sort of, I try to give a little bit different sort of angle to challenges that I think people are very familiar with, but that we're having big, big questions on how to do it. The last part is assurance. I think that Alessio asked a question to Alvaro about it. I think that is a big advantage of neurosymbolic architectures, because having symbolic representation enable you to start talking, so if you think about, I want a system to do X, Y, and Z. Usually we write them is in English, right? When you design an airplane, there is a huge amount of requirements that are written in English. The vehicle shall do X, Y, and Z. And so it's usually these are formalized with some temporal logic or other type of formal languages. And so, it's very convenient to then have representation that are symbolic, because now you can try to prove that what you're designing, in fact, satisfy your constraints. And so, in that sense, neurosymbolic architecture for us are very, very important. And the approach that we're taking is using overarching properties that have been defined by NASA, where you want to define the intent of the system, you want to define the correctness, which is, in the context of known knowns, you will know that it will do the right things, and when unknown unknowns happen, it will not just fail miserably, so you will have an acceptable impact. And then you need to have ways of handling these kind of situations. And so neurosymbolic approaches do provide these very nice opportunities, but you are inheriting all this problem that I mentioned before. If your knowledge was not the correct one and you didn't have enough data, well, now you have neural networks that are not constrained correctly, and you have possible issues on what is the output of neural networks. On the other side, you have you want to connect your logical constraints coming from requirements in the design of these neural networks. For example, in these neural network components, you want to constrain them, and some of these requirements are really, really, really complex. And they talk about different parts of a system, and so you would like them to decompose and sort of map to the right component of the OODA loop. And so this is, in some sense, still an open problem of how to do that in a reasonable approach. The other thing I think is about, in the operation, you would like to be able to, as I mentioned, understand that something is going wrong and do something about it. And so I think that that is one thing that I've seen something, and maybe I haven't looked at all the poster and all the thing, but I think reasoning is something that I still see not done a lot. And I'm also wondering about what are the trade-offs in enforcing constraint and a neurosymbolic level on one side and the reasoning on the other side, right? So for example, it's classical to use sort of what we've seen before, like T-norms and so on, to try to marry, vector spaces with lattices in some sense, right? But to me, it feels right, but at the same time, a little bit, is it the right way? It's very convenient because, well, we only know how to do continuous optimization, optimization of their smooth functions, and logic it isn't. Oh, look, there is this multi-value logic that it's perfect, maps to 0, 1, and is differentiable, and we are good to go. But what are the implications of the choices of the t-norms and so on that you make for training a neural network, constrain it, and to do the reasoning, right? Reasoning in this case would be probably approximate reasoning. And approximate reasoning, I don't know what is the, I've seen very old books about it. I don't know, does it need to change now that we have this, representation? But I think that is very, very important because autonomous systems, you want them to be autonomous because you want them to be able to do something intelligent in the most out of distribution situation, right? If it is in distribution, autonomous systems are just automatic system. We have plenty of automatic system. But if you want an autonomous system that doesn't be, you don't need to go and help every second, really is something that needs to be able to deal with auto distribution. And so, being able to reason and reduce uncertainty is critical. And so that is another part that I'm still trying to understand, the choice of the logics and the implication they have for reasoning. And with that, I wanted to conclude summarizing some of these challenges. They may appear very, very big in many ways, and they are, but you can, if you keep the different component of an autonomous system sort of separate, you can zoom in one specific of this and start asking these questions about, what is the right representation, how to incorporate knowledge, what is knowledge that I should incorporate? Should I incorporate all of it, part of it, which one? Do I go and collect more data? And what, how do I do the abstraction in the right way so that I can come back to the right concrete world? So with that, I can probably close it.
We have time for questions. I had a question on, in my opinion, the uncertainty estimation is quintessential. At some point, we and you and everybody, we actually make decisions not based on the prediction, but based on the uncertainty. Think of problems in which you see new categories and so on. It's basically the planner makes a decision just based on the uncertainty and takes the most conservative actions and so on. Any comments on, that's a threshold, that's typically handled by the planner somehow or even by the decision. So, and I saw Jan was mentioning the energy-based models. I think when we crack that and when we have a logic for those, we'll crack autonomy.
Yeah, uncertainty is one of the, I asked the same question to Alvaro. So robotics has been going on for a long, long time. And a lot of effort has been really put in how do I create a consistent world model. Consistent meaning that as I get more and more information, I should see my uncertainty reduce. Of course, if my observations are more and more uncertain, then I should see an increase. So a lot of effort has gone into that part. And as we are trying to get this symbolic abstraction, understanding how uncertainty propagates and what are the implications in the decisions is critical. I cannot make a decision just because I see another person in front of me. I'm not gonna go and get out somewhere else, right? I observe and see what the person does, and based on that, I will make my decision. So, yeah, without that, to me, how do we fuse multiple sensor data if you don't have statistical understanding? And you would like this statistical understanding propagate up to the symbolic representation, because otherwise there is, any decision can be absolutely correct and absolutely wrong at the same time, right? How do you distinguish what to do and what not to do? It's very, very hard. So, yeah. So, feel free to connect with me. I would like to hear if you disagree or agree, or you have thoughts about how to make some progress towards these challenges.
As a thought, especially for this community, maybe we can come up with a practical challenge problem and next year have, some sort of a mini session on that. Yeah, Alessio.
It's the purpose of the next session. All right. Okay. So I was gonna suggest no. I mean, I agree 1,000% with every single word of what you said, and that's like what my daughter says. So I'm learning from her, but it would be so good if you guys who are closer to the applications than us, perhaps at least some of the applications, could define it something really small that we could begin to tackle, for example, along the lines of these mechanisms and tackle each of these problems that are huge in themselves on a small domain and try to make progress on a small domain, because otherwise it just feels a little bit overwhelming to take on. I mean, this is a program of work I feel for 20 years. And
so having in mind what are the big challenges help you to direct your attention on certain aspects that otherwise are going to be forgotten. But we have some of those specific challenges. You can even work with grid worlds, as Alvaro was showing, and simulate it really well. But when is the right structure? Should that grid work, right? He presented walls, he presented doors. Why should it be square? Why is this precise?
I mean, I guess what I was trying to say is that the real value would be from taking a small program and actually applying all of these aspects, not just safe RL, or not just safe. Try to do the whole thing.
Now, there is a practical challenge on that. You saw my schema with, and also I think Leslie's schema with learned models. In practice, those of you who deployed models, those learned models in practice become smaller and smaller because of robustness needs. Alessio knows at the beginning for taxiing an airplane, probably you've seen some papers from Stanford and us on following a line. There was a full end-to-end following a line. We don't do that anymore. That was too big of a model. Now we do segmentation and localization and so on. So in practice, as we develop the systems, the learned models are smaller and smaller. That's, when you, now, we love to have research on, bigger and bigger models that are robust, but we do that for robustness purposes. And around, it's actually something that's a lot symbolic. And that's also the challenge, through our work with you, we have changed our architectures because of those high-level robustness challenges. All right, Artur, thank you so much for the session, and now we'll have coffee.
Let's have a 15-minute coffee break and come back here. We'll start again at 4:30. Thank you all.
So welcome to the penultimate session. So in this session, we are discussing about some of the challenges, especially when it comes to sort of neurosymbolic approaches, showcasing its potential, and also thinking more generally beyond sort of neurosymbolic only models, sort of thinking about sort of benchmarking or sort of understanding how do sort of other models in the general broad area of general intelligence, artificial intelligence, sort of are benchmarked, how do we evaluate them, what kinds of principles should we be looking into. So the first part of the session we'll have Murray Campbell from IBM, and in the second part we'll sort of have a panel discussion followed by a general discussion with the audience on some of the learnings from this workshop and some of these broader questions that the community is thinking about. So I'll just give you a gist of how this entire thing started. I think around last year, we started with a challenge in Neural-Symbolic kind of setup. We were trying to collaborate with Facebook AI Research or Meta with their sort of text world type of models, the NetHack challenge, but it unfortunately didn't pan out in the way that we wanted it to pan out. So what happened last year was we were looking into sort of thinking about sort of benchmarking and aspects in Neural-Symbolic sort of models where we can sort of have benchmarks that not only are looking into sort of Neural-Symbolic models, but also beyond Neural-Symbolic models, especially encouraging people from the sort of the neural community or the connectionist communities, as well as symbolic communities, to sort of work on tasks and see how we can sort of benchmark in a more rigorous way the contributions from either side and how we can fuse them in the sort of Neural-Symbolic sort of domain. Following which, we have been thinking broadly, more generally, in the context of artificial intelligence. So thinking about how do we benchmark these systems, especially when systems become more complex. Like if you think about large language models trained over massive amount of data with massive amount of compute, how do we think about benchmarking? What are the kinds of things that we need to think about? And out of that, I think some of the steps that we have taken will be shortly sort of discussed by Murray. I guess I shouldn't take more time, and I'll probably introduce Murray to sort of talk about some of these particular discussions that we have been having about thinking generally in terms of benchmarking these models and what does it mean in the general sphere. So without further ado, I'll introduce Murray now. Murray Campbell is a distinguished research scientist at IBM Research. His current research interests include neuro-inspired AI architectures and measurement of progress towards general intelligence. He was a member of the IBM team that developed Deep Blue, which was the first computer to defeat the human world chess champion in a match. He received his PhD in computer science from CMU and is a fellow of AAAI. With that, I'll let Murray take it away from here. It'll be great if we have a warm welcome to Murray.
All right, thank you, Carlo. Can you hear me?
Yes, Murray.
Can you hear me?
Yes.
Okay, good. Thank you. Thanks very much for the introduction, and I'm very sorry I can't be there in person to meet you and discuss this topic, which I think is very important going forward. So the title today is Toward Neural-Symbolic Benchmarks, but as Pranava mentioned, I will be addressing some of the more general issues as well around benchmarking. So to begin, we all know that benchmarks have been include your algorithm's performance on the Atari benchmark. And in supervised learning, the original ImageNet paper has now been cited well over 50,000 times. So it shows the deep interest in this area. So there's a lot of good reasons for the popularity of benchmarks. In fact, performance measures, there were informal benchmarks. And you could even say that the work in computer chess,
Murray, if you just hang on for just a second, there are some issues over here. There are some issues with audio.
Okay.
Apologies for this. I hope. Yeah, I think you should start again, perhaps.
Start again from the very beginning?
No, for the slide, perhaps.
Okay,
I'm
sure.
really sorry. Apologies about this.
Okay, sure. I'll start again. So benchmarks, I think we all know that benchmarks are very influential in AI research. In deep reinforcement learning, for example, you had to present your results on Atari for many years in order to be considered a serious research. In ImageNet, the original paper has now been cited over 50,000 times. So a great interest there. So there's lots of good reasons for the popularity of benchmarks. In fact, even before these sort of more formal benchmarks, there was unofficial benchmarks. And you could even say that Deep Blue, there was a challenge out there in the AI community to beat the world champion, and that's what Deep Blue did back in 1997. But when we get to the more formal benchmarks, they have a number of good reasons for existing. The primary is that you can have a standardized way of comparing different systems. And if you get a new top result on a well-known benchmark, that may boost your chances of getting a paper accepted at a top conference. Clearly, benchmarks are also useful for identifying the strengths and weaknesses of the particular approach that you're taking, which can help you find ways to improve. In many cases, it's useful to compare current AI results with human performance. And in principle, it's possible to assess the progress of the field as a whole by tracking the performance on benchmarks over time. Unfortunately, we sometimes fall a little short on each of these goals. Comparisons are not always properly standardized, and we often focus on aggregate performance rather than the detailed results that would help identifying strengths and weaknesses. And it's really hard to do a fair comparison with human performance, and often the results can be misleading. And many benchmarks are in fact so narrow that they don't themselves provide a useful indicator as to the progress of the field. But nonetheless, we think it's worthwhile to strive towards these goals. So while there are important benefits to benchmarks, there are also many well-known issues that need to be considered when you construct a benchmark. The most obvious one, and one that's been understood for a while now, is benchmark overfitting. Even though the test set is never used to train a supervised learning model, if you continue to focus on the same fixed benchmark for year after year, eventually you tend towards benchmark overfitting, and it limits the ability of the models to transfer outside of the actual distribution found in the test set. And for quite a while, it was common for RL systems to train and test on the same environment, such as in Atari. The second issue is artifacts. Either in labeling, those are kind of obvious. If you make mistakes in labeling, there's an issue, but also in the construction of a reward function in reinforcement learning. This can cause AI systems to, for example, learn surface regularities which aren't really causally connected to the task or the training task that you want to solve. A third major problem in recent years, particularly, is saturation. Once the performance is near the maximum on a benchmark, it's not useful anymore because finally, many benchmarks are focused on just one or a very few types of capabilities, and they don't really do a good job at addressing the breadth that have become clear in recent years. And I'll just touch on these very briefly in this talk, but each of these is difficult, and there are many. One of them. It forces benchmark developers to think differently about the benchmark design and not just use tasks that have been exhaustively covered in the pre-training corpus. While accuracy is probably the most important metric, we have to recognize that there are other metrics that are important when we talk about deploying AI systems, including calibration, robustness, fairness, and so on. And more on metrics, we often focus, as I mentioned on the previous chart, on aggregate metrics across the entire benchmark. And that's often the only number that's reported in papers. But more fine-grained metrics are critical to get deeper understanding of the strengths and weaknesses of our systems. Of course, ignoring resource usage can lead to systems that quote, buy performance in ways that may not be scalable. And a really difficult problem, which we're going to have to tackle head on, is doing a fair evaluation of different kinds of systems. Systems that have different sensors or actuators or energy requirements or motivations or have different pre-training regimens. All of those make it difficult to compare, for example, a large language model with a reinforcement learning model, for example. A challenging issue, perhaps more in the future than now, but I think it will be an issue, is for agents with continued existence. If an agent, when you run it on a benchmark, it updates itself from that experience, as, for example, a human might, then you running it again on the same benchmark isn't a way to generate a distribution of results. It's completely misguided because you have to take into account the learning effects. So that's, while we can imagine right now running many AI systems through APIs where we only have black box access, we don't know what they're using, how they're using that information that when we run a benchmark on a system through an API. Of course, social bias is important, and we need to address and detect and mitigate social biases in benchmarks to ensure that they don't get propagated into the future. And finally, most benchmarks are not very systematic, and they make no real attempt to cover both a wide range of capabilities and difficulty levels, and they include both single decision problems and sequential decision problems. I think this is starting to change, but very slowly. So what can we do? Many of these issues have been recognized and are starting to be addressed. Here are a few examples of some approaches that could be used. There's definitely not an exhaustive list. There are many other ideas out there as well. First, it's important to either hide the test set, although of course this doesn't address agents with continued existence, or evolve the benchmark over time, or generate new tasks every time you run the benchmark. And each of those has interesting costs and benefits. Two interesting examples here are Cholet's ARC and NetHack, which generates new game instances with a reasonable amount of variety each time it's instantiated. And a number of other benchmarks do evolve over time now and add new tasks or new metrics as they over time. A second approach, we should be ensuring that benchmarks gather a variety of metrics, which enables us to have a detailed analysis of failure cases. Benchmarks such as GEM and Helm are both examples of systems that have make a concerted effort to try and gather a range of different metrics on their benchmarks. And Burnell talks about aggregate, not just using aggregate measures. For resource limits, we need mechanisms that will take into account resource usage at different phases of a system's life, including the pre-training, the training, and the test. The continual learning community is well aware of these kinds of issues, and many ML competitions also enforce resource limits in ways that they work, but they may not be easily scalable. And finally, we believe it's important that we start being very systematic about the capabilities that we test, the range of difficulty levels as well. Helm, MLPerf, and Big Bench are noteworthy here, although in my opinion, they're just scratching the surface, and there's a long way to go on this. So one particular type of benchmark that we think would be interesting is a Neural-Symbolic benchmark, where the tasks in the benchmark are thought to be difficult for both neural or symbolic systems unaided, but where we think Neural-Symbolic approaches might be helpful. We can start by asking what kinds of tasks would be appropriate for such a benchmark. One source could be the set of tasks that are not efficiently solved by current neural or symbolic methods alone. Or we can look at problems where the state of the art is well below human level, or we can look at problems where the best results come from Neural-Symbolic systems. An example of the first case is the game of NetHack that I just mentioned, where no existing system can yet match top human performance. And an example of the second case, I would say, is Go, where AlphaZero-like systems are the state of the art and use a Neuro-Symbolic approach, where there's a Monte Carlo tree search combined with neural networks for evaluating moves or positions. So there's some problems with this approach to creating a Neuro-Symbolic benchmark. First, it doesn't consider the rapid progress in neural systems, and many new benchmarks are essentially solved in a relatively short period of time after they appear, often within a year. And second, we're limited to creating a suite of tasks compiled from existing benchmarks, and it may be better to think about ways to create new tasks in addition to those that are already available. So I'll give a simple example of a way to create new tasks, and there's obviously much more that can be done here. One approach is to create tasks of the form Henry Kautz called neural pipe symbolic. So imagine a task that's presented in a non-symbolic way. So the input is either, say, images or video or audio or text or some combination of these. But the task itself is one that is ideal for symbolic processing. So in this case, a neural system can parse the input into some sort of structured form that is suitable for the symbolic system, such as a calculator or a theorem prover or a planner. So if the symbolic part of the task is sufficiently complex, it's difficult for a neural approach, such as a large language model, to be able to perform that task, even when you pull out all the tricks that you have on prompting, such as asking to work step by step and so on. This suggests a pretty straightforward mechanism to generate a large number of tasks that encourage neurosymbolic approaches. And I'll give a couple of examples of this approach. In this first example, the input is a math word problem. And we asked ChatGPT to, instead of solving it, output the equation that will calculate the correct answer. We can then feed this expression into a calculator, for example, via an API, which will, in this case, generate the correct response. However, if we ask ChatGPT to just generate the answer without generating the symbolic task description, it's not able to do the arithmetic correctly and gives an answer that's off by quite a bit. A second example is one where we describe, again in words, a variant of the Fibonacci sequence and ask, say, ChatGPT to generate Python code to determine the 10th term in the sequence. The code it generates turns out is correct, and when you run it, it produces the correct answer. But if we ask ChatGPT to determine the 10th term, and again specify that it show all its work, it makes a valiant effort, but it's wrong. It gets, instead of 4240, 4224. So give it credit for being close, but not correct. So I'll try and wrap up. Benchmarks are important tools for advancing AI research. I think we can all agree on that. To do it right, I've tried to convince you that there are a lot of deep and challenging issues still to resolve for that. And we think that a broad and rigorous neurosymbolic benchmark would benefit the community, both the neurosymbolic community and in the broader AI community. So if you're interested in talking more about this or actually participating in an effort that we've started here, contact me or Pranava, and I thank you. Here's some references for some of the papers that I've mentioned during the talk. Thank you.
Thanks, Murray. I guess we have a few minutes for questions. I probably need some help over here. But if you have any questions or thoughts. Thank you.
I guess this is somewhat of a comment, and I'd be interested to hear your opinion, is that the kind of schema or template you've created for the neurosymbolic benchmark, it seems that it would be almost always best suited for neurosymbolic approaches that are dual, in the sense that the neural and the symbolic are... I'm
sorry to interrupt, but I actually can't hear what you're saying. If you could use the same microphone as Pranava was using,
maybe I could always do that.
No, I can repeat the question, so if you ask it.
That would help, yes.
Basically, the question is, it seems that it's addressed for the dual system, neural, and then message passing with symbolic. Should it not be something that requires more of an integration of the two, I think?
Yeah, so Murray, the question is that the types of benchmarks that are being considered here are mostly dual kind of systems where the message is being passed in some way. But don't you want to consider systems which actually fuse both of them together?
I agree. That's of course a very good comment. I did allude to the fact that the template that I considered for creating tasks was the simplest, perhaps one of the simplest forms of a neurosymbolic system, the neuropipe symbolic. And there are many other more interesting alternatives than that. That was just to get you thinking about what could be done in this space. But it's just a very preliminary first step.
So my worry would be that the class of neurosymbolic systems is actually too wide to submit to a single benchmark. It would be like saying, well, we do benchmarks, not benchmarks for machine learning, either it's very specific tasks. So we would have to, what would be the opinion of Murray on how much we would differentiate different benchmarks for this very broad class of neurosymbolic systems?
So I'll try to paraphrase. So Murray, the question was, the class of neurosymbolic tasks are almost infinity. But so how would you sort of think about differentiating this benchmark with other benchmarks that specifically target some of the aspects of neurosymbolic systems?
Yeah, that's a good question. There's a number of aspects to this that we've been talking about and considering. One is to use the cognitive science literature to try and identify a set of capabilities that we believe are important for intelligent systems. And there's lots of work throughout the past couple of decades on exactly that, using that to identify capabilities, and then for each of those capabilities, identifying tasks that will address either individual capabilities or combinations of them, and be systematic about covering the space of capabilities. A second aspect is to include a range of difficulty levels. The reason for this is that it allows you to better differentiate between systems. If you have two systems, if you have problems all at roughly the same level of difficulty, it will become somewhat of a binary metric, whether or not a system can solve them or not. But if there's a wide range of difficulties, each system will have a chance to find its level in such a range of difficulties, and so enable to better differentiate. I think many of the newer benchmarks, such as Helm or Big Bench, are thinking, very good ideas, have very good ideas, and are working in the right direction. But they're somewhat limited in, first of all, they're focused on language models, which not every system will take input in the form of language. And they are a compilation of existing benchmarks, which, although, for example, Helm is trying to be systematic about what they cover, acknowledge in their paper that they have made many gaps and things still to be done in this space. And I think being very systematic about addressing the capabilities, the difficulty levels, and the methods of presenting problems to systems and finding fair ways to do that will hopefully distinguish the approach that we're thinking about from existing work.
Any other questions?
One question that I had, or maybe a thought is, do you want a benchmark, to compare different neurosymbolic solutions for specific tasks, and how do you manage, comparing with other type of more data-driven approaches. I think that is something that I noticed that on one side you would like to focus on Neural-Symbolic, but you cannot forget about completely data-driven approaches. But data-driven approaches, the metrics that have been used are not completely fair, or are disregarding certain metrics that are very important to be considered when compared to Neural-Symbolic methods. But now, how do you do that, right? I mean, you cannot go back and recreate, for the same benchmark and be more fair. So you have this double problem, right, of comparing Neural-Symbolic approaches among themselves, but at the same time, don't compare with completely data-driven, and at the same time, the fact that the metrics that the data-driven approaches have developed are not fair, or forget certain aspects. So I don't know if there is a good compromise there.
Fantastic. So Murray, the question is about comparing within the Neural-Symbolic sort of approaches, the performance, and across Neural-Symbolic and sort of data-driven approaches, and the metrics which actually associated with neural approaches are not exactly fair. So how would you sort of reconcile these aspects? I guess that's...
Yeah, the fact that because the data-driven approaches came before, they sort of set the metrics. And now the Neural-Symbolic approaches that are sort of maturing later, now they need to sort of fulfill those, but those metrics are very biased towards those data-driven approaches. So you're always in this disadvantaged position of trying to compare to something that is unfair to start with.
Right. So the second part of the question is, so the data-driven approaches, to a large extent, are doing very well, and they have set a very high benchmark. But then they have been developed over a large period of time, and when new Neural-Symbolic approaches come in, they perhaps are unable to sort of compete with these very high sort of performance metrics. So how would you reconcile these two aspects?
So I'm not sure I quite understood the first question. Let me address the second question first, and maybe the first question could be rephrased a little bit. So it is true that many of the standard benchmarks, there are ultra-specialized systems or systems that perform extremely well on Atari or ImageNet or even NNIS these days is obviously, there's very little room for improvement. It's essential to find tasks where there is headroom, where there is room for improvement. Using the same old tasks where high performance can be achieved by known methods wouldn't be a good task for such a benchmark unless there was a method to scale it, to make it more difficult. Imagine a difficulty knob that you could turn. And say, okay, we'll turn it up to 11 to make it more difficult for systems that are acing it right now. So that's, I do understand that some systems will be specialized and perform very well on certain kinds of tasks, but if you have a diverse enough set of tasks, they will probably not do as well on the other tasks, and overall not perform well on the benchmark if they have limited ability to generalize to other kinds of tasks. The first question, I just didn't quite understand.
So the first question is, inside the Neural-Symbolic class of tasks, how would you sort of think about sort of benchmarking those systems? So there is intra-class versus inter.
So, interesting. So imagine having to compare a planner with a theorem prover. Obviously it's in theory possible, but it requires a lot of careful tweaking of the input format and output to do that. I think such systems should be compared on in a relatively standard and uniform presentation of the problems, which would require them to have some sort of input processing to translate between different task formats. In fact, if we're talking about progress towards general intelligence, or whatever that exactly means, and a planner can't deal with proving a theorem, or a theorem prover can't deal with a planning task because of the format is being incorrect or whatever, then it doesn't have the generality that we're looking for, and it will perform poorly on the benchmark. And perhaps a system that combined the two and had a switch between them would score better. Now that seems a bit of a hack, and maybe it is, but that's a first step in creating a more general neurosymbolic system that has different kinds of systems within it to handle different kinds of tasks.
Brilliant. With that, perhaps we'll conclude this session, and let's give a warm round of applause again.